Alright, good morning everyone. We'll be starting in about 3 minutes time. Hopefully you guys can hear me. Alright, good morning everyone. And today's class is just going to be the introductory class into ECNG 3025 DSP, also known as Discrete Signal Processing. And it's just going to give you an idea of what this course is going to be about and what you can expect from this course as well. And coming out inside towards the end of the lecture, if you've got any questions regarding the material of the course or the execution of the course, you can ask them at that point. Or if there are any relevant questions as you see the material on the slides, you are free to interrupt and ask any questions during the point of the lecture to get any clarification that you require as of such. Oh, right, let's get started. So what's going to be our course being discrete signal processing, and basically instead of using continuous time signals, which we saw in ECNG 2011 signals and systems, we're now going to be focused more on discretized time systems instead. And that means we'll be focusing more on sample signals and their relevant samples as to respect to discretized time, such that it means that it will happen at definite points in time instead of it occurring across all points in time instead. And basically we will be dealing with discretized time signals. So if you haven't seen a discretized time signal, it's basically just a digital signal, and it's just going to be a one-dimensional vector of magnitude values, where each position vector represents the instance of time the sample was taken. And even though you might not understand that now, while we keep on going through the lectures in particular, you'll actually see visual representations as to how the signal actually looks, and then we can correspond it back to our definition and also observe it mathematically to see, okay, how do we form that relationship between the mathematical notation and the visual representation. Of course, the last part of the discrete signal processing part is going to be the processing, which is going to be involved with us doing signal manipulation regarding these discretized time signals. Now, in comparison to continuous time signals, which we saw, which were basically a pain to manipulate, because we had to do differentials, integrals, and a whole set of signal manipulation for like time reversal, time shifting, and so forth. Discretized time signals is a lot easier to do these manipulations because you got the advantage of it being a one-dimensional vector, and all the mathematical notations for these are relatively simple. There's no fancy differentials, there's no fancy integrals to learn, there's no long processes to do and so forth. You have the advantage of using computers in this course to actually speed up your work and to actually verify all your work and so forth throughout the entire course. One thing to note as well is that this course is very straightforward, so there's only typically one way of approaching the entire problem, and those ways are basically shown step by step throughout all the lectures in this course, and you basically get an idea of how to approach everything up front, and there won't be like any hidden kind of questions that you'll be getting and of such. It is a very straightforward course, and there's no wait for any sort of kind of weird questions to appear or for it to be answered and such and so forth. Everything is straightforward. What you see in this course is what you get. So, like I said, because we're dealing with discretized time signals, that means it's more like digital signals, and it's a lot easier to manipulate than our continuous time signals that we saw all the way back in year 2. Conversely, even though we're also dealing with the time axis, there may be times that we will need to go into the frequency axis, but this is, instead of being continuous frequency, it'll be discretized frequency. And as we go on through the material in the course, you'll realize discretized frequency is a lot easier to manipulate as well. So there isn't any fancy long differentials or long integrals and so forth. It's just straight numerical manipulation, and it's a lot easier to do than all this continuous time integral and differentials. So this here is a definition of what DSP could actually be about. What the definition basically says is that instead of using analog components, we're all going to be focusing on digital components. And because of the invention of processors and computers, this makes our processing a lot easier to do nowadays, as of such, for any sort of discretized time signals we'll be dealing with. And since the world has moved from all the way back from 1974 to 2020 from analog to digital, it's a lot more important as to learning how do we transfer those analog continuous time processing techniques into digital discretized time processing techniques, and how do these techniques actually optimize our way of doing things that tend to be really long in continuous time, as well as how do we go about speeding up and making things more efficient with respect to discretized time in the digital domain. Even so, that because we're dealing with a lot of digital signals, that means we can deal with a lot of high frequency signals in the realms of gigahertz and possibly even higher than gigahertz, as of such, as the frequencies keep on increasing due to technological trends and improving technology. Now, where do we find discretized signal processors or any sort of discretized signal processing? And basically, once you own any sort of digital device, you basically have some sort of DSP inside it, even if it's for some sort of simple type of processing or complex type of processing in particular. So nowadays, a lot of our phones have like a set of DSPs in them, basically for your audio processing, which represents when you speak into the microphone, it actually transfers your auditory signal, which is an analog signal, into a digital signal, and it does a lot of amplification and signal processing to clean up the signal and so forth. We also have GPS, which is basically global positioning, which tells us our real-time location and so forth. That also relies on DSPs, cameras, tablets, home entertainment systems, digital televisions, sound systems. All of these use DSPs in some form or fashion to achieve the required outcome that the device is intended to deliver. So basically, mostly everything that you're using nowadays is going to involve some sort of DSP, unless you have a really analog type of piece of equipment that's not going to be relying on this and so forth. Even so, for people who may be thinking about, okay, well, the power applications nowadays, that tends to be a little more analog, they actually are moving towards digital because now there's actually computerized breakers where you can actually program the breakers themselves to respond to different sorts of conditions and for them to trip back on after faults occur and they have been resolved and so forth. So the world itself is moving a lot more from the analog perspective towards the digital perspective throughout all these technological trends and increases in technology and so forth. Now, the nice thing about this course is that it's not always limited to one field. Once you learn the theory and techniques in this course, you can apply it across a multitude of fields. So, in particular, people who are looking to make money, because yes, everyone wants to get rich and so forth, you can apply DSP techniques into financial applications for actually analyzing the stock market fluctuations. And you can actually use these techniques to predict when the stock price is going to rise and when it's going to fall and so forth. So you can actually make an informed decision when to buy and sell. Similarly, for people who are looking towards going into a security-related aspect field, a lot of the security applications nowadays uses a lot of DSP techniques for doing encryption and decryption and for protecting your information and so forth. Also, like things like geophysical applications or geolocation applications, those use a lot of DSP techniques. Communication system in particular uses a lot of DSP to get rid of noise because they are focused on the quality of experience for their signals. So that means you need to have clear video, clear audio, and so forth. Control systems, because the world is moving from linear control systems to non-linear control systems because they are getting an increased range for using non-linear systems. They're also focusing more on the DSP techniques as to how we can get better signal quality over longer ranges in particular. And there are so many more areas that you can actually apply all of these DSP techniques to. So the techniques that you learn in this course, they can be applied across almost any sort of field that you can think of once there's some sort of digital application towards it in some form or fashion. Now, I need to backtrack a little bit to explain how we're moving from the analog signal processing to the discrete signal processing at this point. So we know basically that if we need to build some sort of analog circuit, we have gotten some resistors, some capacitors required, an operational amplifier and so forth, and then we had to connect it with physical wires to ground and all inputs and outputs and whatnot and form our interconnections. Because of this, that means that if we need to do any sort of modification to this circuit, that we will physically have to go into the circuit and remove components or reroute wires and so forth, which tends to be pretty troublesome. So normally when you build an analog signal circuit here for any sort of processing, it tends to be only for a single use. Because if you need to reconfigure it, that means you're going to have to redesign and rebuild the entire system entirely. And the limitations of this is basically, because it's a single use sort of circuit, you're going to have restricted accuracy. And that means that any sort of external factors, being time, temperature, noise, and so forth, all of these interfere with the circuit. As of such, you may not get the desired accuracy that you require. Also, because it's a single use, you're restricted to one range, so you don't really get a huge dynamic range and so forth. And like I said, the system itself is going to be very sensitive to noise. You can't really alter this because this is a single, it's only suited for one sort of process. And if you have to do any sort of alterations or adjustments, that means you have to rebuild and redesign the entire circuit and so forth. It doesn't really work for non-linear applications, and as the circuit itself gets pretty huge, that means you're going to have increased cost because that means you're going to have to route more wires, more parts, and so forth and whatnot. Also, with analog circuitry, there's a limited speed because they're restricted by the physical components as of such. They can only operate up to a certain frequency in particular because of the limitations of the semiconductor materials used for building such components. However, because we'll be focusing on discretized time signals, so we're not going to be focusing on continuous time signals in this course and systems, we're just going to be focusing on discretized time systems and signals and so forth. We basically operate on samples of these continuous time signals, and this basically just gives us a digital approximation to the actual continuous time signal that existed. These samples themselves are typically represented by binary numbers, but as we know, binary numbers can be transformed into any numerical base. So as of such, for all purposes, we'll be dealing with decimal numbers because, let's face it, trying to deal with binary numbers is going to be a lot more tedious than if we're dealing with decimal numbers, which we're accustomed to using every single day in our lives. And once we have these samples here, the combination of the samples here makes our digital signal as of such. And like I said, we'll be focusing on only using discretized time signals and systems throughout this course. And that's the name of the course, Discrete Signal Processing or Digital Signal Processing as such. So a discretized sinusoid, its visual representation looks like this here in the following figure. As you can see, it still has the general shape here of a sine wave, but instead of it being continuous where we can obtain any value at any point in time, we took samples at fixed points in times instead. So the spacing between these two samples here is what we're going to be referring to as our sampling time, because the sampling time tends to be constant throughout the entire process. So if we say here that the sampling time was like at every 1 second, this would be at minus 20 seconds, we took a sample of the continuous time signal. Then at minus 19 seconds, we took another sample, minus 18, minus 17, and so forth as we keep on going. These samples here represent the instantaneous value at that particular point in time at which we took that sample. So this basically says at t here equals to minus 20, we took the instantaneous magnitude value of the continuous time signal and represent this as a sample in a discretized time signal, and so forth as we keep on going throughout the entire samples. For our case here, because it's not digital, this is because we haven't made any numerical assignments throughout the entire thing, because we can see here it just goes between 0 and 1, but we haven't applied any magnitude here to say, okay, what's actually going to be the representation for actual signal as of such. So until we actually start applying physical units onto the y-axis here as well as the x-axis, that represents our sampling time between two successive samples, as well as the actual required magnitude of the signal, then we can say that this forms a digital signal as of such. Once we don't have these values for our y-axis and x-axis, it's not going to be a digital signal because it's more going to be more of an abstract signal, because we can't accurately represent it back to its continuous time signal counterpart. And because we're going to be dealing with digital signals and it's just going to be a one-dimensional vector values, and to give you an idea what that would look like, let me write it on the screen to give you an idea. It's like if we have, let's say we have a digital signal here equal y, it's going to be like 0, 1, 2, 3, 4, and it's just going to be a one-dimensional vector of these instantaneous values. So we can say here at this point that's going to be like t equals 0, and then here could be at t equals 1, t equals 2, t equals 3, and so forth, to give you an idea, okay, these are the instantaneous values at these particular points in time. And because it's just a one-dimensional vector of values, that means it's a lot easier to do any sort of signal manipulation, because now we can just add and subtract these values directly and multiply and divide them as of such. There's no long sort of mathematical manipulation required. We can just do direct signal operations on these values as is, because of the nature of this signal being digital. Because of this, this also gives us a lot easier and more flexibility to manipulate the signals as required, and we can design systems a lot more easier as well to actually do these processes. Now, There are specialized microprocessors that you may see in particular that also do all of these signal manipulations on these numerical values here. You have actually been exposed to one of these so far, being the FPGA in year 2, which is actually a specialized form of a digital signal processor. There are also standalone processors, which you may have experienced in micro-P, which tend to be like, okay, these are good for simple applications, and they're like more complex processors like your GPUs or graphical processing units in your computers and in your phones nowadays. They actually do all the heavy processing to actually give you a nice visual experience on your screens. So basically, how the discretized signal processing operation occurs is that it just converts some sort of analog signal into a digital signal, and it forms a binary sequence as of such from doing this conversion. Once it is in the digital domain, we just basically perform all the signal processing operations in the digital domain because it's a lot easier to do. And once we get the required output signal, we just need to convert it back into the analog signal form for us to basically see or hear it, or get some sort of tactile feedback as of such. So in this example here, it's basically like if we're doing a communication between two people using a cell phone. It's like the audio that you speak here goes through an analog to digital converter to convert the auditory analog signal into a digital signal. And once we have the digital signal here, it's then processed to clarify it and make it a lot more clear and remove any background noise and so forth. And once we get the required output from this DSP here, we just convert it back into an analog signal to drive our speaker so that we can actually hear what the person is saying as of such. Now, because these signals here are basically just going to be one-dimensional vectors of instantaneous magnitude values, it's a lot easier to store these and manipulate these as of such. And you don't require to build any fancy circuits. It's just like you just put on one processor and you say, okay, we can just reprogram the processor as required to do any sort of processing functions as of it. And because of that, that means you drive down the cost considerably for building any sort of circuit, because you have this reprogramming and a lot more flexibility as to how you want to actually do your processing for your signals. And as of such, you can implement a lot of complex circuitry that may have been represented in analog domain into the digital domain instead, just on one piece of circuit, instead of having to buy multiple components and having to route all these wires and so forth. It's a lot easier to do, a lot easier to implement, and it saves a lot of time and cost as well. Also, advantage of this is that because there's also optimization, that means you can actually do a lot more fast algorithms and matrix-based processing to actually speed up your processing as well as parallelize your processing to handle big amounts of data, and you can get this in a relatively short frame of time once you have a high enough frequency. And as of such, because you're dealing with these digital signals, you can actually get a very high accuracy and you'll get very high reliability, meaning that you'll also always get the same value no matter what. So things like noise and so forth isn't going to be affecting your circuit and so forth. No external factors like temperature and whatnot will actually affect your circuit as well, because it's all going to be in the digital domain. And as of such, that means instead of having a single use circuit, you now have a multi-use circuit, so you have a lot more dynamic range, and you can actually do a lot more applications, being you can do parallel signal processing, you can do speed up sequential processing, you can actually do a combination of serial and parallel as you wish, so it's full reconfigurable, and you have a lot more applications and opportunity to do any sort of processing that you require. Just use one circuit itself. Now, just to give you an idea of what the inside of one of these circuits look like, and yes, it looks a little bit scary, but it's not going to be very scary at all once you start seeing the material in the course. It's like basically we just have a whole set of different blocks inside here that will be dealing with different aspects of the signal processing. So like these interfaces here will be responsible for doing the digital to analog control as of such. And the frame shifter and the RAM input here is just going to be like memory storage and small signal processing manipulation to shift the signal as required. Then the DSP processing here is going to be handling the bulk of the processing that is required to be done on the signal. And once we finish with all the processing inside here, we will have a RAM output buffer to output it in chunks of data if it's going to be output in real time, and then we just format the data here at this point, and then we just output it towards our output here and so whatnot. So yeah, like I said, the circuit looks kind of scary, but actually when you start breaking it down into its individual components, it's actually quite simple. So there's nothing to be scared about. It's just we're going to be going from one block at a time to understand how the signal processing is done on a microscopic level and then at a macroscopic level for the entire circuit. Another example here is where we combine parallel processing with this processor here and this processor here, and sequential or serial processing with these two processors here as of such. You tend to see this kind of processing more in medical equipment, because they'll be like, okay, these two processors can handle some sort of data here, but we also are restricted by doing sequential processing because we still require some of the data here and some of the data here to be actually processed and whatnot. Alright, so getting down to what is going to be expected of the course. This course is basically going to be taught mainly by me, Mr. Anil Maharaj. Dr. Mudin may step in from time to time to teach. If not, the course will end up being solely taught by me as of watch. The sort of topics that you're going to be dealing with in this course in particular, it's going to be like block diagrams, difference equations, and Z transforms. We'll also be focusing on the fast Fourier transform and spectral windows that are used for the fast Fourier transform. We'll also be looking at spectral analysis, which is basically going to be digital frequency analysis on discretized time signals. We'll also be using MATLAB to actually illustrate and visualize how these signal processing techniques can be used, as well as actually getting real-world experience as to how you can actually implement these signal processing techniques on an actual digital system as of such. We'll also be looking at designing digital filters in the sense that there's going to be low-pass, bandpass, and high-pass filters using something referred to as infinite impulse response, or IR, and finite impulse response known as FIR digital filters. And we'll be looking in particular as to the design techniques as to how do we design for an IR filter and an FIR filter accordingly throughout the course. We'll also be looking at it throughout the course how we can actually implement these filters using MATLAB, and how we actually be using it on some real-world signals as such, so you get a lot more real-world experience as to how you actually can apply digital signal processing techniques onto real-world signals itself. We also be looking at other sorts of applications for DSP itself. So for example, we could be looking at JPEG compression, which is image formats. So like from how you take an image from your camera and how it's actually formatted into a nice small size image. Sorry, a nice small memory size image while maintaining maximum quality from what you took using your camera. We're also looking at something known as DTMF signaling, which is basically how do you dial on your phone and how those dial tones are processed in order to represent which number you actually are trying to call. And we'll be looking at some audio processing techniques as well, in particular through the problem sets with real-world audio signals and actually how can you process them using MATLAB itself and some signal processing techniques as of whatnot. For the last lecture in this course in particular, we were looking at something referred to as video processing techniques, and it's going to be focused on more on image formation using graphical processing units and whatnot. But we'll get into more detail into that once we start reaching those lectures in particular. And finally, we'll be talking about advantages, disadvantages, and limitations of using digital signal processing versus continuous signal processing. For this course, the course breakdown is going to be an 80% final exam and a 20% midterm exam, where both of these exams are going to be open book in nature, due to the COVID-19 situation. Traditionally, the midterm exam has always been open book, and it has always been 2 questions or 3 questions that's going to be dispersed over the 20% allocation. And you will have, one correction here. This isn't going to be a 1-hour duration in-class exam. This is going to be, so this is going to be this time frame is going to change accordingly, so you might get like a 12-hour duration to do the midterm as of such. So this is to be changed. So depending on the regulations for online classes that's been going to be re-administered and so forth by the university, this is going to be a 12-hour in-course exam, so you got 12 hours to actually attempt and upload your submission as of such, and it's going to be fully open book. Same thing with the final exam, it's going to be 12 hours to attempt, and it's going to be 5 questions on that final exam, and it's going to be fully open book as well. There are no homework assignments, but it is very advantageous if you actually do the problem sets throughout the entire course, because the type of problems that you're going to get in the problem sets are going to be the same type of problems that's going to appear on the in-course exam and on the final exam as of such. The problem sets also give you, as the last questions, some physical real-world applications as to how you can actually apply your discrete signal processing techniques onto real-world signals and how they actually are modified or manipulated out of such, and you actually observe the effects as required. The classes for this semester, it's going to be Monday from 8 to 9 a.m. and Wednesdays at 8 to 10 a.m. I know here it stays like it's going to be 13 weeks of lectures, but it's going to be less than that. Most of the time it's going to be 9 or 10 weeks of lectures. We'll have 1 week for the in-course, currently scheduled for March the 3rd, which is a Wednesday. We also have 1 week for any sort of review that we need to do regarding any sort of topics or any problems that we're encountering throughout the course that requires a lot more clarification. There's going to be 4 to 5 problem sets in particular for all the material in the course and whatnot. Once the problem set has been released on the previous week, on the following week we'll be doing the problem set on that Wednesday session in particular. And those problem sets will be reflected when we actually attempted it in the tutorial sessions. So there's going to be like 3 to 4 tutorial sessions in particular. There may be 5 tutorial sessions or 6 depending on how the classes are going in regards to pacing and so forth. The only public holiday that might actually affect class this semester is going to be Easter Monday, because unfortunately we have no carnival this year, so I'm not too sure how that's going to work. I think we'll be teaching as normal as required. For anyone who's looking for reference texts for this course, these are the list of texts that you can use throughout the entire course. The one I recommend the most to use, it's going to be this one here, known as Signal Systems by Oppenheimer. So you want this one in particular. That's going to be the best text that you can ever get for any sort of signal systems applications that you need to do regards to continuous time and discretized time signal processing. The other books are also nice, but this one here is going to be the best one you can actually get for any sort of information you require. And this here is just going to be our contact information in case you need to email us for any queries or any sort of clarification throughout the entire course as of such. The extensions here, please ignore them because we're no longer physically on campus, so you're going to have to email us accordingly, but we do monitor our emails quite often, so you tend to get pretty fast responses as of such. And all our consultation is going to be fully online, so like I said, you're free to email me any questions throughout the entire course. Throughout the live lectures, you're free to interrupt me and ask any questions. If you are watching the video afterwards because you are unable to attend the live sessions, because these videos are recorded in real time and they're immediately published once the live session is finished, you're also free to leave questions in the comments down below, and I'll always respond to you guys accordingly within a reasonable time frame, of course, because like I said, I understand that you guys also have other courses, and I also have other things to do regarding for other courses as well. So you tend to get a response within like 1 to 2 days maximum. Most of the times, if it's like something that's a really short answer or something like that, you could get a really short response and whatnot, and you'll get it like within a few hours at most. So the course outline is also on my learning to give you an idea of all the information in a summarized format that was delivered here in this introductory lecture. And all the course material, being all the lectures and so forth, is going to be delivered on my learning as of such. For people who may not have access to the course because of registration issues and whatnot, you can feel free to ask your colleagues to send you the information via any sort of communication medium as of such. But all the lectures for this course are going to be delivered on this YouTube channel, and it's publicly accessible despite your registration status. So you can attend these lectures on YouTube as of such. You can log in and ask any questions. You're not going to be restricted by registration status. If once you're here to learn, you feel free to interact and ask any questions as of such. And don't be hesitant to ask any questions once you don't understand anything. Ask immediately. If you don't want to ask immediately, you can always email me afterwards to ask any sort of questions that is required, and you need some sort of clarification as of such. Alright, so that brings us to the end of the introductory lecture. Are there any particular questions that need to be answered at this point in time? Well, it looks like a lot of people are good with whatever we've seen here. Okay, so because I typically tend to get this question from one person every now and then, the pass rate for this course last year was 100%. To give you an idea of how well the course actually is. And like I said before, there is a very straightforward approach in this course. There is no sort of trickery here in this course that can be done. Everything is really straightforward. Whatever you see in the course material is what you're going to get and what is going to be straightly tested in your midterms and in your final exams. The solutions of the problem sets will be posted on my learning afterwards when we do the problem sets sessions as of such. Also, because the problem set sessions will also be live recorded, these will also be videos that will be immediately posted afterwards once the live session is finished on the on YouTube here. So you can actually view them at any point in time. Even if you happen to get locked out of my learning, they're going to be here on this YouTube channel, so you can access them no matter what. Similarly, because I got this question asked last semester, the course material on my learning and so forth and the videos here will not be blanked out when it's time for any sort of exams, because like I said, those exams are going to be open book, so why blank out the material? You already had the material, it's going to be here fully for you to access at any point in time. So you don't have to worry about that. Even after, when the course is completed, the videos here are still going to be here regardless, in case you need to refer to it at some point in time. I will post up a set of past papers coming down to the end of the course. But if you do require me to post up the past papers earlier, that also can be provided as of such. I can also post up the past papers in particular from now, so you guys can have an idea of what sort of questions that will be coming in particular. What I can tell you is the more recent past papers, I probably don't have any solutions to them as yet. But it's possible that for any of the tutorial sessions, we can actually focus on particular past paper questions once we finish with the problem sets, so that actually you can get a lot more live experience as to what sort of questions and how to approach them regarding your midterm and your final exams as of such. And that's what I did with the last year course offering, where once we were finished with the problem sets, I moved on towards actual final past paper exam questions. So they got a lot more experience as to how to handle those questions and how to go about answering them. So I'll be taking the same approach regardless. Yes, it would include past midterms as well. So it's going to be basically the sort of questions that you would expect on the midterm. And typically, the material you get tested on the midterm will not be repeated on the final unless I state otherwise. So you'll know in advance like what sort of questions or what type of topics you're going to be getting in advance on the midterm and final in particular. If the library website only has up to 2011 to 2014, I will see if I can make provisions for them to get the more past papers, but during the problem sets and tutorial sessions, I will be referring to questions from more recent years. So from, I believe, 2016 going up to 2020, you will get those questions in particular. So you get more recent versions of the questions regardless. Oh, one other thing I know, for anyone who actually pulled this lecture, there was a slide indicating that there was a MATLAB exercise, but we're not doing that this semester. There's no MATLAB exercise to worry about. All right, any further questions? Currently, the midterm is set for March 3rd. Depending on the course loading for you guys, it can go 1 week before, 1 week after, but typically it tends to be at the same date. If not, it will go 1 week later, as of such. Alright, so if there are any further questions, feel free to leave them in the comments down below, or you can directly email me those questions as such. And like I said, all the live lecture sessions are going to be done right here on YouTube, so even if you do happen to get locked out of my learning due to some sort of administrative error or registration issue and so forth, you can still attend the classes here freely, and you can also participate in the classes. You could just log in and type in the chat to ask any questions regardless. So until then, I will see you guys on Wednesday for the first lecture. So take care, be safe, and I will see you guys soon. Later.